Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying application of derivatives lecture 4. In this lecture we'll be talking about local maxima, local minima, global maxima, global minima and first order derivative test. Okay. So let's begin our lecture with the local global maxima minima, right? So let's say we have a graph like this one. If we talk about these 2 points, these are the local maxima. If we talk about these 2 points, these are the local minima. Why? Because we are just talking about the vicinity points. Let's say if we talk about this particular point, let's say this value is 5 for a particular value a, x equals to a, right? Now if we talk about these 2 points, basically the vicinity points, values are actually a little lesser as compared to 5, let's say 4.99, right? So these values actually are lesser than 5, so we can say that among these points, basically in this vicinity, this particular point is having a local maxima, right? That's why it's called as local, right? Because we are just comparing the local values, we are not comparing the overall values of the function, we are just comparing local values, right? Similarly over here we have a local minima, over here we have local maxima, and over here we have local minima, right? This point is clear. Now one thing interesting over here is, just like our monotonicity, we don't have to consider only differentiable functions, we have to consider all sorts of functions over here. Maxima, minima can be calculated, can be found out for all sorts of functions, right? That you have to keep in mind. Now, if you talk about global maxima or global minima, in that case, if the function is ending over here and if the function is starting from here, you can see that this particular point is having the highest value and this particular point is having the lowest value. So local maxima or local minima may or may not be the maximum or minimum value respectively. They may or may not be, right? So we can have a different value altogether depending upon the endpoints and starting points. Okay. Now, based on the discussion in the previous slide, how can we define local maxima minima mathematically? Okay, so let's first talk about local maxima. Okay, so let's say we have a graph like this. This point is, let's say, A, and let's say the vicinity points are A minus H and A plus H, right? Let's say the function is fx. So this particular value would be f of A. This particular value would be f of a minus h, and this value over here would be f of a plus h, right? Now if you want to have a maxima at point A, what can we say? F of a should be greater than f of a plus h, and f of a should be greater than f of a minus h. These two conditions should satisfy simultaneously to have a local maxima over here, right? Very simple, basic most definition. Now if you talk about local minima, in that case, we'll have a graph like this. This point is again A. The vicinity points are A minus H and A plus H, right? This value is f of A. This value is f of A minus H. And this value is f of A plus H. Now in this case, f of A should be less than f of A minus H, and f of A should be less than f of A plus H. Both should satisfy simultaneously to have a local minima at this point. Okay, local minima. Now if we talk about the global maxima, global minima, what difference is there? We just have to check the endpoints as well. Firstly we have to check these points, and then we have to check the endpoints as well to see if these values are comparable to that one or not, right? So let's say if we have a local minima over here, and I'm also checking these endpoints, if these endpoints are having lesser value as compared to this local minima, in that case I'll consider that as the global minima. If not, then this would be local minima, also global minima. Okay, now let's take one example. Let's say we have a graph like this. Filled circle over here, open circle, filled circle, and moving on. Okay, so let's say this particular point is A, this particular point is B. This value is f of A, and this value is f of B, right? So we have to understand if we have a local maxima or local minima at point A or B. Okay, so let's first talk about point A. So this is the value f of a. If we talk about the vicinity, so f of a plus h would come somewhere over here, f of a minus h would come somewhere over here. Both are actually lesser than f of a, so we have a local maxima over here, right, at this point. And now if we talk about point B, then we have FB over here. If we talk about f of B plus H, it seems to be bigger than f of B. So f of B plus H is bigger than f of B, right? Now if we talk about B minus H, then f of B minus H is actually lesser than f of B. It's actually lesser than f of B, right? So we don't have any local minima over here. Why? Because in that case, it should have been like this. Only in that case, we could have said that B is having a local minima. But over here, we are having this. So we cannot say that f of B is having a local minima. Okay. Now let's talk about stationary and critical points. And in the previous slides, we have chosen points like A and B to find out if they have a local minima or local maxima. But how were we choosing those points? We were choosing those points because they were either stationary points or critical points, right? So that's why we were choosing them. But what is the criteria for choosing those points only? So we have observed that in case of any function, local maxima or local minima is happening at a point where derivative is either 0 or the function is non-derivable at that particular point, right? When these two conditions are happening, in that case we have observed local minima or local maxima, right? So that's why we have defined stationary points and critical points. Now what is the difference between them? So in case of critical points, we have either derivative as 0 or the derivative is not existing. But in case of stationary points, we are talking about only differentiable functions. So that's why we are talking about those points only where derivative is 0. So in stationary points, derivative is 0. In critical points, derivative is 0 or the function is non-differentiable at a particular point. Okay. So stationary points in reality are a subset of critical points only, right? Just because we are talking about only differentiable functions over here. In this case, we are talking about all sorts of functions. Over here, we are just talking about differentiable functions. That's the main difference, right? And now that we've understood the basic definitions of local maxima, local minima, stationary points, and critical points, let's have the first special case of differentiable functions, that is local maxima once again. Okay. Now, let's draw the graph once again. So in the earlier case, by the basic definition, we were talking about in terms of function values. We were talking in terms of function values. There was no derivative involved. We were just talking in terms of function values, right? This was f of a, this was f of a minus h, this was f of a plus h, and these two have to be lesser than this one to have a local maxima over here, right? That was the basic definition, right? Now in this case, let's try to define in terms of slopes or derivatives, right? So at this point, we can see that f dash is 0. Let's say this point is a. This is x equals to a. So f dash a equals to 0 over here, right? That's how we have defined. Now we can see that over here slope is positive and over here slope is negative, right? If slope is positive, we can say f dash, let's say this is a minus h. So f dash a minus h should be positive, and over here, let's say this is a plus h. So f dash a plus h should be less than 0. So derivative is positive, then becoming 0, and then going negative. In that case, we say that we have a local maxima, right? In the previous case, in the basic case, we were talking in terms of function values. Over here, we're talking in terms of slope values because we're talking about differentiable functions. Okay. Similarly, we have a second case, that is local minima. Now in this case, reverse is happening. So we have this point A over here. This is x equals to A. So f dash A equals to 0, right? That's how we have defined. Now in this case, over here slope is negative, over here slope is positive, right? So if you talk about A minus h and if you talk about A plus h, so f dash A minus h should be less than 0 and f dash A plus h should be bigger than 0, right? Should be positive. So if these three conditions are meeting, then we can say we have a local minima for differentiable functions. Okay. Now the third case is, we have two parts in third case. Okay. So we have something like this, or we have something like this, right? Okay. Now in this case, what is happening? F dash is becoming 0 at one single point. Okay, just one single point. Let's say this value is a. So f dash a equals to 0. It's still 0. But what is happening? Over here slope is still positive. Over here slope is still positive. So if we talk about a minus h and a plus h both, so f dash a minus h is positive and f dash a plus h is also positive. Now in this case, again, at this particular point A, f dash A equals to 0. But over here slope is negative, slope is negative. So if you talk about A minus h and A plus h, so f dash A minus h is less than 0, f dash A plus h is also less than 0. So in this case we say that we have an inflection point. It's neither maxima nor minima, it's actually an inflection point. And now let's talk about point of inflection formally. So point of inflection is a point where curvature of graph changes. So what do we mean by that? So we have a graph like this. So we can see that over here curvature is facing downwards. Over here curvature is facing upwards, right? And it is decided by this particular point. So on the left hand side of this, curvature is facing downwards. On the right hand side of this, curvature is facing upwards. So this particular point is called as point of inflection. Now some people confuse that, okay, we can have only f dash as 0 over here. It's not. We can have a curve like this as well, right? So this particular point is not having f dash as 0, right? We can see that it's still positive, but over here curvature is downwards, over here curvature is upwards, right? So that just basically means the point which is separating two types of curvatures. Point which is separating two types of curvatures, that is the point of inflection. It doesn't have to do anything with the f dash. It doesn't have to do, okay? And now let's solve this example. Discuss the extremum of fx equals to 40 upon 3x4 plus 8x cube minus 18x square plus 160. Now, the first step is to find out the critical points. What are the critical points? Critical points are the points where the function is either non-differentiable or derivative is equals to 0, right? So let's talk about the second part, that is derivative equals to 0. F dash x would be minus 40 upon 3x4 plus 8x cube minus 18x square plus 160 whole square multiplied by derivative of this one because of chain rule, right? So that would be 12x cube plus 24x square minus 36x, right? Now this has to become 0. Now if it has to become 0, only numerator is going to affect, right? There is no point of considering denominator playing a role in making this 0, right? So we have to just be concerned about the numerator. So in numerator we have 12 times x cube, or let's say 12x times x square plus 2x minus 3, right? This is equals to 0. So this is 12x multiplied by x minus 1 and x plus 3, right, equals to 0. So x equals to 0 or x equals to 1 or x equals to minus 3. These are the 3 points where this derivative is becoming 0. That's just one part of the equation, right? We have to also consider second part, that is where the function is becoming non-differentiable because we have something in the denominator, right? We have something in the denominator. Okay. Now, if we talk about denominator, this is a biquadratic, and we know that biquadratic usually look like this one. So they might be cutting x-axis at 4 points max to max, right? That is the maximum they can cut, right? But I cannot see that we are able to factorize this one very easily, right? It might be very random numbers, so we might not be able to factorize this equation easily to find out the roots, right? So how do we understand if they're cutting this x-axis or not? It might be possible that the biquadratic looks like this one, or it may be possible that it's looking like this one. So we don't know how it's looking. So how do we understand if it's cutting or not? So we have to first find out these local minimas, right? Local minimas, local maximas. So if the least value is also below the x-axis, then we can say it's actually cutting. If the least value is also below the x-axis, then we can say it's actually cutting. If least value is above the x-axis, then we can simply say that it's not cutting. None of the points are cutting because this one is higher, this one is not the least value, assuming that this one is the least, right? So if the least value is above x-axis, in that case we can say the function would look like this one, and it's always positive. So we don't have to be bothered about if the function is differentiable or not, right? So again, to find out the points of local minima and local maxima for this particular function, we again have to differentiate this one, right? So we have, let's say, gx equals to 3x4 plus 8x cube minus 18x square plus 160, right? And now if we differentiate g, we'll be getting g dash x equals to 12x cube plus 24x square minus 36x plus 0 equals to 0, right? To find out the critical points so that we can find out the minimum value and see if it is cutting x-axis or not, right? So this becomes 12x times x square plus 2x minus 3 equals to 0. So this becomes 12x x plus 3 x minus 1 equals to 0. So we have got the points as x equals to 0, x equals to minus 3 and x equals to 1, right? So we have to check at all these points what is the value of this function, right? So g0 equals to, that would be 160 only, because this would be 0, this would be 0 and this would be 0, so it comes out to be 160. Now if we talk about g1, that would be 3 plus 8 minus 18 plus 160, that also is positive, right? Because we have 160 over here. If you talk about g of minus 3, then we have minus 3 raised power 4 and we have 3, so 3 raised power 5, that is nothing but 243, plus 8x cube, that is 8 multiplied by 27 minus 27, because we have minus 3, so minus 3 cube, okay, minus 18 into, that is 9, right, and plus 160. And now if you calculate this value, this also comes out as positive. So basically what is happening, g0 is positive, g1 is positive, and g of minus 3 is also positive. So what do we mean by that? So we had a graph like this. So let's say this point was 0, this point was minus 3, and this point was probably 1. At all these 3 points, derivative was 0. These were the critical points over here, right? And we can see that all these values are actually positive. So the biquadratic equation is always lying above the x-axis. It's not cutting x-axis. So when it's not cutting x-axis, we can simply say that there is no point of indifferentiability for this particular function, because we were finding out the points where this can become 0. And since this function is not cutting x-axis at any point, that's why we can say that there is no critical points generated due to indifferentiability of this particular function. Okay. Now coming back to this derivative once again, we can say for sure that this denominator is always positive based on the recent calculations we have done, right? This biquadratic is not going to cut x-axis, so it's not going to become 0. It's always positive. It's always above x-axis, right? So our f dash x becomes minus 40 into 12x taken as common over here, we'll be getting x square plus 2x minus 3 whole divided by, let's say this is some k square, positive quantity, right? Always positive. Now f dash x can be written as minus 40 into 12x multiplied by, this is x minus 1 and x plus 3 whole divided by some k square, right? Now this reminds me of wavy curve method, right? This is 1, this is minus 3 and this is 0, but we have a minus sign over here, right? So we have to find out the signs of this particular f dash x, right? That's how we are going to define local maxima or local minima, right? So since we have a negative sign over here, it would start from minus plus minus plus. So at minus 3 on the left hand side we have positive slope, on the right hand side we have negative slope. At minus 1 on the left hand side we have negative slope, and on the right hand side we have positive slope. At 0 on the left hand side we have positive slope, and on the right hand side we have negative slope. So based on which you can find out if we have a local minima or local maxima, right? Simple. And now let's solve this question. We have fx equals to ln x by x, where x is positive. Investigate the function for maxima and minima. So we have to find both local and global. Okay. And this is your homework question, because this is the easier one as compared to last one. Okay. So today's lecture was till here only, and the next lecture would be the last lecture of AOD. So let's meet in the next lecture. Thanks for watching.